Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yeah, it's up to you. Okay. Time. Okay, traders.
Anyway, it's our pleasure to host Leonidas Galanis today. Working for Redistribute, and the work he does fits nicely at the intersection between distributed systems and database. For all people here.
Okay. Welcome to my talk. Feel free to interrupt me whenever you have questions. So, my name is Leonidas Galanis, and I've been working with David DeWitt in the database group in the University of Wisconsin. And I'm going to talk to you today about the focus of my thesis, locating data sources in large distributed systems. First, let me try to motivate my work by looking at the web as it is today. So you have two parts to it. There's the surface web, which is the part that's accessible to web search engines and is being crawled constantly by search engines, and you can query it very efficiently using Google, for example. And then there's the second part of the web, which is, can you all hear me, by the way? Okay, good. And the second part of the web is, some people call it the hidden web or the deep web. And this is the part that's inaccessible to search engines and resides usually in database backends behind some servers. And some studies have estimated this part to be 400 to 550 times larger than the surface web. And you can't actually query this part of the web using Google, for example. So I want to query this data. And there's two ways to do it. One is to download the entire thing to a central place and run queries against it. And the problems with that approach is that it might be not scalable and it might be not possible because the deep web may not be able to be downloaded. And the other approach is to push the queries to the data sources themselves. And in essence, this means we have to do distributed query processing. So there are many challenges to doing that. One of them is security authentication, interface agreements, and all this. My thesis has focused on the problem of scalable data source locations in distributed systems. And I think this is a critical component for building a distributed query processing system in the internet scale. And it's the first step before doing distributed query optimization and distributed query execution. And I'm going to talk about this problem and try to illustrate it. So where do I expect to find web data in the hidden web? In my thesis, I assume that I have a large number of distributed, independent, and autonomous data sources that look to the outside world like XML repositories, in the sense that they store XML documents and they export some kind of XML query interface, like XPath, for example. And examples of such data sources can be relational database management systems today. Almost every vendor is trying to put XML functionality into their systems. And there are a lot of vendors also that sell XML database systems that can serve as database backends for the deep web. And then there can be XML documents on a web server, or even WinFS that's supposedly going to be exporting an XML view to the outside world. So let me try to illustrate the problem. I have a large number of data sources in the deep web. New data sources become available, others change their data. And I want to run queries against all those data sources. One way is to build a data center, download the entire web, and run the user's queries against this data center, which can be done or may not be able to be. You can do it or you can't do it. Depends on what the data sources give you as data. The other way, the naive approach, is in order to ensure that you actually run your queries on the entire data set, you just send your query to everybody. But of course, this is not scalable. What I would ideally like to do is, given a user's query, determine which data sources have results for this query and send this query only to those data sources. And this is the problem of locating data sources in such distributed systems. Now, before I go on, I'd like to talk to you a little bit about XML and XPath that I'm going to be using throughout the talk. So this is an example XML document. It's supposed to hold data for a library. And XML has, as you see, markup, elements, and attributes that surround the data. In this case, the catalog element contains all the books that are available for checkout at the library, and the reservations element contains all the books that have been checked out by library patrons. Now, this is an XPath query. This particular query retrieves all the books that have been authored by Tannenbaum and are in the catalog element of the library. It means all the books that have not been checked out and are written by Tannenbaum. What the XPath processor would do is it would start matching the path in the document in this way, and for each book that it retrieves, it will match the corresponding predicate down here, and it will return as a result for the query the book that has been the second book here. Now, another interesting XPath operator is the double slash here. Oops. And what this will do is it will return any book that has been written by Tannenbaum anywhere in the document. In this example, it will return this book also. And another interesting and useful XPath operator is the star operator, which basically means any tag. And this query would not only return books written by Tannenbaum, but would also return articles and whatever Tannenbaum has written, basically. So I've talked to you about the naive approach of running queries on the deep web. Now I'm going to present you with two alternative designs for locating data sources. First one is the peer indices approach, and was presented in the Conference of Advanced Information Systems Engineering in the summer of 2003. So, and let me try to provide a history of how this approach was actually developed. I was in the University of Wisconsin. I was part of the Niagara project, which is an internet scale query processor that runs XML queries over XML data it has downloaded from the internet. The specific problem we had in this system was that we had a large number of documents, and we wanted to run an XPath query against the entire collection of documents. And of course, running this specific XPath query over each document is not effective, so you need some kind of an index. And in the Niagara system, we used an XML search engine, which is basically an inverted index that maps XML elements and text keywords to documents with some structural information. So, for example, for this query, book author equals Tannenbaum, that retrieves all the books written by Tannenbaum, the search engine would process the inverted lists from the search engine, using some operator, and we would determine which documents would have results for this specific query. And the rest of the documents we don't process at all. So when I started my thesis, I extended this approach to the distributed case and introduced the peer index, which is basically a list which maps element names and attribute names to a list of nodes that have those attributes and element names in their data. So for this specific query, each node maintains a peer index. And for this specific query, what will happen is that first we take the book node list, and we find which nodes have book in their data. Then we intersect with the author node list and narrow down farther, and then with the Tannenbaum node list, and find out that nodes 4 and 5 have the relevant data to this query. Now, the question is, how do we build those peer indices? Sorry about that. I wanted to have a system that was consisting of independent autonomous data sources running Niagara servers. So one way to build such a system is through ad hoc network formation. So what happens in this case is a node contact some other node, and they build neighbor relationships and so on. And when you have a query, and at the specific node, if you don't do anything else, you have to flood your query to all your neighbors in order to get all the results that are there in the network. And of course, this does not scale well, and you see how bad it is. So instead of just joining and becoming neighbors, nodes exchange data that allows them to build this small peer index. And this way, when you have a query at a node, you consult your peer index, and you can immediately send the query to nodes that will have results for your query. Now, I'll take you through an example of how this is actually done in the system. Suppose that we have two nodes. One of them is an auctioning node that auctions off paintings with prices in here, and the other one is an artwork gallery that sells sculptures. Now, for some reason, those two nodes want to come together and cooperate. So what will happen is that node 1 will send node 2 its metadata tags, element and attribute names, and some interesting keywords. And the same thing will be done by node 2. And this way, the nodes will build this peer index that you see here. So this allows node 1 to know that sculptures are present on node 2. Now, when a third node comes along, suppose that we have an auctioning node, auctioning site that auctions off sculptures. This node will also contact one of the other nodes, node 2 in this example, and will give it its tags and its interesting keywords. And node 2 will forward this message to node 1 and will reply to node 3 with the information that's already in the network. And in this way, nodes augment their peer index and know about each other's data. So whenever you submit a query to any node, for example, a query to node 2, this particular query retrieves all the open auctions that involve paintings. Node 2 will consult its peer index and will rule out node 3 as a candidate for receiving this query. Now, as you can imagine, when nodes become part of the system, those lists grow linearly. And we introduce horizons as a way to bound them. Let me explain to you what horizons do in this case. For example, node 1 here has a horizon that has whose size is one hop in the network, which means that node 1 knows only about node 2 and does not know about node 3. Not knowing about node 3 means that node 1 does not store any information about node 3 in its peer index. And in this case, a query originating at node 1 that needs data from node 3 will be first sent to node 2 using the peer index, and then node 2 will forward the query to node 3. So what I'm trying to illustrate here is that if you can bound the information in the peer indices in order to bound their size, but there's trade-offs in the number of messages you need to get to the actual data sources. So, for example, yeah. Right. So semantics can be built as a layer on top of this. I'm assuming that the nodes have an agreement of what they are actually talking about in their data. So if you want to build semantics, you may have to introduce themes. You may have to introduce a collection of things that mean price, for example, and build that as a layer on top of the system. Maybe you could do something automatically, but most of the times, some of the times you won't be able to do anything automatically. You have to actually look at the data itself to see if a specific tag means the same thing in all data sources. But I'm not doing this in my research. What is in which one? Mm-hmm. So in this horizons, node 2 is forwarding to N1 knowledge about the keyword itself, and it's masking, and knowledge about N3 is not stored in the peer index of node 1. But the fact that there's a keyword sculpture on N3 is reflected on N1 here. Which, oh no, the fact that, let me see here. So N3 has sculptures, and in the full index case, you can see it here. But in the horizon case, N2 thinks that sculptures are only present on N2. And N1 thinks that the sculptures are only present on N2. And so the general idea is that when you have a horizon and you have some nodes within the horizon, and then you have some nodes on the boundary of the horizon and some nodes outside, when you have a query issued at node 1, and the data is on the nodes that you see marked here, node 1 will think, for example, that node 8, the data on node 8 resides on node 7, and the same thing for node 4, and will forward the query to the nodes on the boundary. And then the nodes on the boundary will forward the query to the nodes outside the horizon, which will incur extra messaging. And finally, the nodes will respond with query results. So horizons are a way of bounding the peer index information. And there's another way of bounding the number of keywords, but I'm not going to talk about that. You can ask me offline about that. It's a kind of a technical detail. So I've built the system and run experiments on it. I've built a network of XML search engines that have those peer indices, and that also have the inverted indexes that do structural queries on XML documents. And I've built it using Java and BerkeleyDB. And I took data from eBay, about 45 gigabytes, and ended up with 450 megabytes of data and about 450 megabytes of inverted index on each node, and about 8 kilobytes of peer index. And each node was serving about 60,000 to 70,000 documents. And each document essentially describes an auction of a specific item. And I ran experiments on our departmental cluster, and each node had about 12 users, each of them submitting XML queries, XML search queries requesting items in a specific category. And the nodes joined and formed an ad hoc network that had a 9-hop diameter and an average of 3 neighbors per node. And there were many, many nodes with few neighbors and very few nodes with very many neighbors, which is typical of peer-to-peer networks. And these are some of the results I got. So this graph shows you the query throughput in the system in queries per minute. On the x-axis, you have flooding on the left, which basically means no peer index at all, and full information on the right, which means in the peer index that everybody knows about everybody in the system in the 100-node network. And then in the middle, you have horizons of varying sizes. And as you can see, full information has the best performance, and the performance degrades as you limit the information that resides in the peer index. And flooding is really, really bad. So the lessons from this experiments is that you can get up to 20 times faster throughput, better throughput using just an 8K peer index per node, which is very important. And flooding is surprisingly bad. We didn't expect flooding to be that bad in just 100 nodes. And what we can say is that knowledge of where your data is very crucial in doing distributed query processing in such environments. And there's a clear trade-off between the size of the peer index and the performance of query processing. Yeah? It's independently derived for each node. And it's horizon, right. And in their experiments, the horizons is measured in terms of hops, network hops, in terms of a radius, maximum network hops to other nodes, beyond which there's no data recorded in the peer index of the specific node. Well, in this experiment, all the nodes had all the keys that were in the data in all nodes. So the horizon just limited the node IDs that were stored in the peer index. I'm not sure if you're asking this. Right. In this experiment, but if you had the larger network, you potentially would use the size that's going to be distributed, the size of information that's going to be distributed. Okay. Yep. Right. 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 Mm-hmm. Well, in our experiments with a real system, we could only go up to 100 nodes, 200 nodes. So full information was just 8K. So I would stay here if I would want to build this. The next one is like 7.5K, which is not measurable, but is not an interesting difference, but it shows how the performance varies when you are forced to take more hops to get to your data. Yeah. Right. Right. So the data from eBay has basically the same schema in my experiments. So I took the data and put some XML tags that actually say which thing is a price, which thing is a description. And the heterogeneity was in the categories each item was belonged to. So each server in the experiments was assigned a spectrum of categories that it was serving up. So this was how the data was used. Any other questions on this part? Okay. So now I'm going to talk about distributed catalogs, which was presented in the Very Large Databases Conference in the summer of 2003. And before starting, I'll try to contrast it to the previous approach. In the peer indices approach, we had a trade-off in the size of the peer index versus the number of network messages that were actually incurred during query processing. And there was uncontrolled replication across nodes, meaning that each node was managing its own view of the network. And network formation was not that good because you require an order of n squared network messages to build a network of n nodes with full information on the peer indexes, which is not bad if you see the query performance, and since it's a one-time cost, it's not bad either. But in the distributed catalog service, we want to follow a different design approach. So we partitioned the peer index across nodes, and this way the number of network messages is independent of the peer index size. So I'll show you why this is. And we use controlled replication for load balancing since the peer index is partitioned. And we try to make network formation more scalable by leveraging DHC technology, and I'll talk to you about that as we go on. So the concept of the catalog. What's the catalog framework going to do for you? You have a large number of data sources again, and each data source, what it does is it processes its data and creates some catalog information. In the case of XML, the catalog information contains elements, and for each element and attribute in the data, it creates a summary information that's node specific. So, and this catalog information is fed into the catalog service. The catalog service, for now, is a concept that when given a query, it will take its elements, attributes, and predicates, and it will give you the data sources that you actually have to visit in order to get results for the query. The rest of the data sources, you don't need to bother at all with this query. And in this part of the work, I propose building the catalog service using distributed hash table technology. So what are distributed hash tables? They're basically hash tables that have this interface that allows you to put an object using its key and to get it back using its key. And specifically, those hash tables are implemented as a peer-to-peer network, as a structured overlay network, in that neighbors choose specific nodes as neighbors. And each peer in this network is responsible for a specific key range, which is dynamic. And put and get gets routed to the appropriate node. So example distributed hash tables are can, chord, and pastry. And there are many more. There's been a lot of research in this field. And they have very desirable properties. So they're very scalable. And they require an order of log n messages for put and get in an n-node network. And the storage and bandwidth grows linearly with a number of nodes that join the system. And nodes can join and leave dynamically, and these take care of maintaining those good properties, and nodes can contact any node in the network that's already in the network and join. So distributed hash tables are a good thing. There's been a lot of research, and I expect them to get better and better over time. So how can I use those distributed hash tables to build a catalog service for locating data sources? The first thing I have to do is define the keys and the objects. After a lot of thought, the keys, the design we came up with is the keys are XML elements and attribute names, and the objects that are stored in the DHT are node ID and summary pairs. And summary contains all the paths leading to the associated element with the summary and an optional value summary. And I'll go into an example to show you how this is actually built. So let me start the example by considering a data source that's a library. And this again has a catalog element that contains all the books that have not been checked out. There's a reservations element that contains the books that have been checked out, and some membership elements that have some prices associated with this membership. So what are the keys I derive from this data set? In this case, it's all the element and attribute names in my data. So, and the objects are built as follows. For book, I record all the paths in the data that lead to book. For author, I do the same thing. I record all the paths to the data that lead to author. But since author has values, I also include a value summary to reflect those values. And the value summary can be any of your favorite value summaries, like Bloom filters, histograms, ranges if it's numeric values. And I do the same thing for price. So what do I feed to the DHT? I give it this. The key I derive from the author tag name, and the object is the summary tagged with a node ID. Now let's put in some other data sources in the example. I have 3 libraries, 3 bookstores, and some other data sources that have irrelevant data to this example. And let's assume that bookstores have data that looks like this. There's books, and since you can buy those books, there's a price associated with them. And note here that price is below the book element, whereas price in the libraries was below the membership element. So the summaries would look like this. There's only one path to author, so book, bookstore, and one path to price, and the corresponding value summaries. Now the DHT maps keys to an identifier space. And let's assume that the keys are mapped as you see here in the slide. And similarly, nodes map to the same identifier space and thus become responsible for a specific key range. In this case, node 1 is responsible for storing catalog information about author and book ISBN, and node 3 for title and price. And of course, these key ranges are dynamic, so they change as more nodes join the system. And the DHT takes care of that. And now I assume, for simplicity, that all nodes have joined the DHT and are about to upload the catalog information onto the catalog service. What will happen is, I'll show you the example for author and price. Node 1 will process its data and send summary about author to itself, because the node 1 is the catalog node responsible for author catalog information, and it will send price summary, the price summary to node 4, which is responsible for price information, and it will tag each summary with its node ID. Question? And node 2 will do the same. It will process its data and upload the catalog information to the corresponding nodes, and guided by the DHT, of course. And node 3 will do also the same thing. Now, from the viewpoint of the catalog service, how does the catalog information, how is the catalog information stored on a node? So node 1 is responsible for those 2 tags in the data, and it will store, it will receive summaries that look like this. So, and it will store the data in a B tree, and the key is derived from the summary as you see here. And this is basically the inverse path in the data. That's why the key of the B tree is the inverse path in the data. And each key maps to the corresponding node IDs and the value summaries for this specific element. So now, if a catalog service receives a query, an XPath query to resolve, like this one, bookstore, book author equals Tannenbaum, if there are no special operands like double slash or star, just a simple key lookup will retrieve all the value summaries that we need to, and will tell us which nodes we need to send this specific query to. If the query looks like this, basically there's a double slash up front. You start a range scan using the lower bound key author book, and then you check all the value summaries and of the nodes IDs you find along the way. If the query is more complex, you have double slash in 2 places of the query. You start a range scan using the author key, and for each key that you retrieve, you check that it has a reservations element in it, and then you check the corresponding value summaries. So 2 examples to show you how this works. The first query retrieves all the books authored by Tannenbaum, and let's assume that it's submitted at node 3. Now, using the target element of the path expression, author, the DHT takes us to node 1, which is responsible for author catalog information, and node 1 tells us that nodes 1 through 6 have author in their data. Then using the predicate, author equals Tannenbaum, let's assume that we can further narrow down the number of nodes that we need to send the query to node 2 and node 5, meaning that only those 2 nodes up here have Tannenbaum in their data. So this is the answer to node, yeah. They did. The author summaries. So they actually the summaries include the summaries are in this case the summary can be a Bloom filter that you can give it this predicate and tells you if data on a node has Tannenbaum in it, and of course it can give you false positives. Not all the values. It's basically summarizing all the values using some of the common techniques. Okay? So basically, probing the value summary using this predicate, it can tell you that only node 2 and node 5 have Tannenbaum in their data. Might have, right? But it cannot give you a false negative. So basically, the value summary will further narrow down the nodes you have to visit. So, and then the query is sent to just those 2 nodes. For the more elaborate example, this query retrieves all the prices for books authored by Tannenbaum. And there's 2 branches in this query. So we start to submit the query again on node 3, and we use the target element of the first branch, and the DHT takes us to node 4, which is responsible for price catalog information. And there, the catalog service on node 4 tells us that node 2, node 3, and node 4 have only prices below book in their data. Libraries have also prices in their data, but it's not below book, so they're not included in this list. Then we use the target element of the second branch, and we go to node 1, which is responsible for author catalog information. And there we use the Tannenbaum predicate, and we find that only node 2 needs to receive this query. And the answer goes to node 3, which submits the query to node 2. So a little bit about how the system evolves dynamically. So there's those nodes are already in the catalog service. A new node wants to join the catalog service, and it can contact any node in the system, and it finds its place in the identifier ring and becomes immediately responsible for the author catalog information. which eventually will move to node 1. And at the same time, it injects to the catalog service its own catalog information. When a node leaves, some other node becomes responsible for the catalog information. So, yeah.
So if it leaves by just going down or being disconnected,
If it leaves gracefully, it's
it needs to, in order to transfer,
right.
perhaps not a slow fashion transfer.
Well, it's not going to be gigabytes of data. Yeah. But if it leaves gracefully, all is okay. You can transfer the data. Right. Otherwise, you can use some of the facilities present in the DHTs and keep replicas of catalog information and revert to those if it just dies. So by using the catalog service, by using the DHT to build the catalog service this way, there are certain scalability issues that arise. And I'll talk to you about those now. And they stem from the fact that there's going to be non-uniform element access during catalog lookups. Some of elements are more popular than others, and that's natural. And this non-uniform element access will lead to non-uniform load distribution of requests to the catalog service. And the solution is adaptive key management. Basically, what you do is once you detect an overload, you create new keys and you redistribute the summary information. And I'm going to talk to you about two techniques, splitting and replication. So splitting, I'll talk to you about this now. Let's assume that node 0 is responsible for catalog information about price. And let's also assume that price can be found in data that looks like this. So you have prices of cars, prices of bikes, prices of boats, and so on, right? So you can imagine that price is going to be a very popular element and it's going to be looked up very often. So the request rate on node 0 may become prohibitively large. So node 0 will initiate a split. What it will do is it will take the summary information for price and split it this way by creating 4 new keys by grabbing the parent element of price. And those 4 new keys will be assigned to 4 new nodes by the DHT. At the same time, each node maintains a meta key map, which records basically the split that has taken place. So node 0 puts this entry up here in its meta key map. And next time some other node asks for price catalog information, it will also get as a response this entry. And subsequently, it will, based on the query, use the alternative keys to request catalog information. And this way, the load is distributed across all the 5 nodes. So the red part of the load corresponds to queries that end in /price, which are still handled by this node 0, and the rest of the load goes to the 4 new nodes. And this approach is called split replicate. And because the information because node 0 still maintains the information that's also present on node 1 through node 4. If we don't want to maintain duplicate information, we just throw it away. And then the load for queries that ending in /price will also be transferred to those 4 new nodes. And this is called split toss, and it has a disadvantage that queries that end in /price will have to go to all 4 new nodes to get full catalog information, and so incurring more network messages. So, and you'll see how this affects performance. Replication is simple. Again, request rate increases, and node 0 requests a number of new keys. In this case, 2 new keys to which it maps price. And those 2 new keys correspond to 2 new nodes, and the meta key map entry looks like this. And subsequently, when nodes receive this entry, they will do a round-robin request on those 3 keys, and the load will be distributed evenly, approximately, across the nodes. So, how is splitting compared to replication? So splitting adapts faster because it uses the structural information in the data, and it's better during updates because you need to only update at most 2 replicas. Of course, it's specialized because it needs hierarchical data to work, and it's not effective in marginal cases where the hierarchy is not deep enough, for example. But in marginal cases, you can always revert to replication, which is more general and is always applicable, but it requires more messages during updates, and it does not use structural information if you have it. So to some performance experiments. I used real-world schemas from www.xml.org that registers XML schemas that actually companies use with their XML data. And I found 30 schemas of varying domains: banking, arts, transportation, music, and all of them had about 3,500 unique tags and many tags in common. And all those schemas have about 16,000 unique paths from root to the leaves. So, and I generate a large pool of about 1 million queries from this data, containing both / and star in the queries. And I took the code simulator and I put catalog query processing layer on top of it and did some detailed time simulations for catalog requests. So it was a two-phase experiment. The first, I implemented the catalog structures and run query workloads against them to take measurements for single site operations. And then I plugged these numbers into the simulator and simulated 5 different networks. And so in this case, there's no the actual data is my metadata. There's no data. I can't get the data, but I can still create catalog information using the metadata and some distributions for the data. The catalog does not store data. I'm not interested in store data. The catalog stores metadata. So users in the experiment submit XPath queries, and we had about 10 users per node. And I tested 4 different strategies, one with no load balancing the requests, one using split replicate, split toss, and replication, which created 1 replica at a time when there was an overload. And the load balancing action was triggered basically using a threshold on the queued catalog requests in the system. So the first results, this show you the average response time of catalog queries in the system. The best performer is split replicate, and followed by replication, which does worse in the more demanding networks because it does not adapt as fast. Split toss does, yeah? No, I expect the centralized database to perform faster if I can scale it as much as I want. I mean, I'm trying to see what I need to do to build a peer-to-peer system that implements this catalog service. A centralized database is a different design. Well, these figures contain network delay in them. So centralized database, if I can scale it infinitely, is definitely going to be better, right? But I mean, I don't have a specific, I don't have a specific amount of servers I can use. I can't really constrain that. So I'm just looking at the distributed system itself. So as I was saying, split toss performs really bad because of queries that look like this, where you have a double slash at the end of the path expression, since they generate on the average many more messages than the other lookups. And Chord, of course, performs worse. Just no load balancing performs worse, and it would perform even worse if it weren't allowed to drop some requests, which you don't see here. So the second graph shows you the throughput of queries achieved in the system. Again, on the x-axis has the varying network sizes, and the y-axis gives you the throughput. Again, split replicate maintains the best scalability characteristics in the throughput case, and split toss and replication do also as well. And no load balancing does not give you scalable throughput. Yeah. Yeah. So the workload, I take all these elements that I find in those schemas, and I assign them. I create queries based on some probability that that an element will appear in a query. And I tried different workloads where the elements that are farther down in the hierarchy are more likely to produce queries, and where there's a uniform distribution of queries among the elements. And all of them gave me similar graphs. I need to mention though that if you don't have double slash in your queries, then split toss and split replicate will essentially perform the same, because they won't incur extra messages. But double slash in queries is a very common feature in XPath queries, so they're there with some probability. I don't have
So XPath is still glorious.
Yeah.
So does your system handle the whole?
No, my system handles the part of it that it needs to actually find the data sources. So if you have some fancy operation on an XPath branch, it will just take the branch and will tell you you can find data in those data sources, and then you can send the query over there, and it will do this fancy operation on the data source per se, not on the catalog. So if you're computing an average or a minimum, you will get the data sources that you have to visit in order to retrieve all the data to compute the minimum.
Solve the hard bit about distributing XPath. Solve this bit. The rest is scalable.
Well, I think that solving the problem of locating the data source is the first step to doing everything else. And by knowing where your data is, then you can build more scalable strategies to run your queries. And I'll have some slides on that later on my third part of the thesis, and you'll see an example of that. Yeah? Right. So the bottleneck in this experiment is the request rate on individual nodes. Nodes that receive a large number of requests get clogged, and they can't, and they bring down the throughput of the whole system. So there's some popular elements that are looked up frequently. So if you don't do load balancing, then this becomes the bottleneck. The processing of the catalog requests becomes the bottleneck. It's a CPU, yeah. No, it's a CPU, because catalog information is very small and fits in the CPU. I'll show you the sizes. Fits in memory, and I'll show you the sizes on a later slide. So it's the processing time for catalog requests. Of course, as you can see here, the response time increases, and some of this increase is due to network latency, because when you go from 500 to 5,000 nodes, you need more hops to access the actual catalog node when you issue your catalog query, because there's this log n factor in the DHT. So this slide is kind of explaining the previous ones. On the x-axis, you have the nodes ranked by the number of the requests they receive, and in this case, we just have only the 51st of the 5,000 nodes. And on the y-axis, you have the number of requests each node receives. So with no load balancing, there's a few nodes that receive very many requests and become the bottleneck of the system. When you enforce load balancing, split replicate and replication even out the curve, as you see here. And split toss also evens out the curve, but it generates more messages, and that's why you see the gap relative to R and SR here. So a little about the catalog sizes. The average catalog size in our experiments was about 12 to 15 kilobytes on each node. And the load balancing techniques increase the average catalog size by about 2 kilobytes, which is nothing. Another important factor here is the metakey map size. In the split replication case, it's 35 kilobytes for each node, because each node maintains essentially the same metakey map. and about 6 kilobytes in the replication case. So it's more in the split replicate case because there's a recursive splits and you need to keep around more information when you split based on data. Another interesting metric is the, yeah? Question? Yeah? Right, in this specific experiment, there's only 30 schemas, but in the real world, you may have 30,000 schemas. The actual number of what? Yeah. Well, I could only get 30 schemas. That was the reality. But I expect to be more than 30 schemas around there. I expect it to scale because the catalog information is going to be distributed across all nodes. So for this experiment, it's just 15 kilobytes. What if it is a megabyte? It's not big information. It's not a big amount of information because the catalog information itself is distributed across all nodes. And once you add nodes, the system scales automatically because you get redistribution of the catalog information. Yeah, so the maximum catalog size is also an interesting measure because this is the worst case nodes are going to be expecting. So in the 5,000 node network, the maximum catalog size was about a megabyte for this specific experiments. And in general, it's not expected to be very large. So some related work. Yeah, I'll skip that in the interest of time, and I can talk to you about that. I'd like to talk about some other work I've done. So this is the third part of my thesis. It goes back to your question. Doing distributed aggregation in a peer-to-peer system. So I'll show you 2 slides. I'll explain the problem and very briefly and show you what we actually achieve. So imagine that you have the catalog service and it allows all the data sources to discover each other. And you have some buyers in this network that want to buy a specific digital camera and find the retailer with the minimum price. So what you do here, you see a complex XPath expression that computes the minimum of the price of a specific model and returns the URL of the retailer that has this price. So what you can imagine is that the catalog system will find the retailers for you, but each buyer will in turn query each retailer to get the price and compute the minimum. And what you'll have is this mesh here. And the number of meshes is going to, if the buyers and the retailers grow linearly, the number of meshes is going to grow quadratically. So what we propose is use an aggregation layer and assign a peer in the network the maintaining of this minimum, this specific minimum of this specific digital camera model. And then buyers would just query the specific peer, and retailers will update their price. Whenever they update their price, they'll inform this aggregation maintainer about the new results. And I tried to evaluate this scheme using a distributed commodity trading scenario. And I built a simulator that simulates distributed commodity trading between traders. And this particular case, you see the test results from a 100,000 node network with 100,000 node traders and varying number of commodities you see in the x-axis. And the system with the aggregation layer constantly outperforms the system without the aggregation layer. And if there are a large number of traders per commodity, as in this case where there are only a small number of commodities, the system without the aggregation layer does not work. So you need, even if you have the catalog service, you need to do more if you want to execute more complex queries in a scalable fashion. And I've recently built this system using Pastry and DBXML, and I'm currently running experiments on the cluster again using a similar scenario. And some other work I was involved with is as a part of the Niagara project. And Niagara is an internet query system that works on XML data, and I've worked on the query engine and the client-server prototype of the system. I also did some theoretical work on defining an XML query algebra that we used in our system and are using now. And I also worked on the inverted list engine of the Niagara system. So to conclude, I've presented you the problem of locating data sources, and I've presented 2 solutions to tackle it. I think it's an important problem in a growing internet, and it's the first step in doing internet scale distributed query processing and distributed query optimization. For doing distributed query optimization, you need to figure out how to maintain statistics over your data and how to make servers exchange those statistics in order to make the declarative queries work in a distributed environment. This research I see it as a part of the field of data-centric distributed systems, and there's been a lot of talk about the internet becoming data-centric and about finding ways of making it data-centric as opposed to host-centric as it is now. So, and I guess that's it. If you have any questions. Right. So I haven't looked at trust in this environment, but I think data sources that want to receive queries are willing to share with the rest of the world some summary that will make queries go to their site and eventually generate revenue for them. So it's not a scheme where you give out your data. You just give out the schemas you're using and some summary of how your data looks like. Excuse me?
In the aggregation example,
Mm-hmm. Right. So somebody might report a lower price, for example, than they actually have. Yeah. Yeah, that's going to be an issue there. I mean, I don't have a solution to that in this particular research. Yeah.
Very distributed.
Mm-hmm. In print.
Suck all the data to one gigantic place.
Right.
Something very specialized.
Right. So Google needs to do a specific thing. It needs to compute the PageRank, and in order to compute the PageRank, there's no clear way to do it in a distributed fashion. And Google does not care whether it has the most up-to-date information. So in this scenario, I assume that data sources will want to receive queries, and since Google cannot keep the most up-to-date prices, for example, then data sources are not guaranteed to get queries through Google. They want to receive the queries directly. So the catalog service will point to the data sources that will answer the queries. Up-to-dateness is one thing that this scheme makes better than Google, for example. Yeah. Yeah. Actually, my office mate has recently published a paper. Actually, it's not published yet. Has a paper that does distributed PageRank calculations using a similar schemes. So, but in a distributed fashion. I don't think you could do it as efficiently as Google does it, the full text indexing in this fashion. Mm-hmm. Right. In this design, there's no. Mm-hmm. Right. You can't. Right. You have to distribute. You have to essentially distribute in your entire index. But this is not what I'm trying to do here. Right. But you can actually do it, and you can. We have a system at Wisconsin again that distributes the keyword index across nodes, the actual index that Google has, and my office mate, as part of his thesis work, has written some Google-like PageRank on top of it. So there is a distributed indexing system that does what Google does in distributed fashion. But I guess it's not doing this as scalable as Google does. But essentially, Google is a distributed system itself. It has a large number of data centers doing the same thing. So, any other questions?